Hello, I'm Ryan Campbell. Today we're going to talk about the card game No Thanks. This card game is played with a special deck of cards where each card is numbered from 3 to 35 with no duplicates. The goal is to collect fewer points than the people you are playing against. So in our extensive game, each card will count as a negative payoff. The player with the highest payoff wins. We will go through an introduction with rules of the game, scoring, 3 example rounds, and talk about their Nash Equilibria, and then a conclusion with weaknesses of the Nash Equilibria of the rounds, and then think about, do the Nash Equilibria actually help us win? As we prepare for the game, we need 3 to 5 players. Each of our examples is going to be 3 players just for ease of our trees. Each player gets 11 chips that are worth 1 positive point each, so those are going to help with our payoffs. We shuffle the deck of cards that are numbered 33 through 35, and we deal 9 cards randomly out of the game. No one gets to see what 9 cards have been removed from the game. Play begins with player 1, who will choose an action to either take the face-up card or to put a chip on it, in which case the play passes to player 2. All players have the same action set of yes, take the face-up card, or say no thanks and put a chip on it. The players continue in this manner until someone has picked up the card. When they pick up the card, they also receive all of the chips from the round. We then flip over the top card of the deck and start the next round. It is very important to note that if a player does not have any chips when it is his turn, then he must take the face-up card and, of course, all of the chips on it. When we flip a card to start the new round, the person who picked up the last card is the person whose action it is. It's their turn to start the new round. For payoffs, we have end-of-game scoring. So when all cards have been taken, we calculate the scores for each player. For any cards that are not in a sequence, so they are single or individual cards, we count their face values as their scores. If cards are in an unbroken sequence, also known as a run, you only count the lowest card in each sequence. Recall that all these scores count as negative payoffs. Then we add as a positive score 1 point per chip. For example, Figure 1 has all single cards that sum to 74. That player has payoff negative 74. Figure 2 has a single sequence, or run, with lowest card 16. We only count the lowest card in the run, so that player's payoff is negative 16. Figure 3 has a mixture of individual cards and a run. We count the 11 from the run, and the individual 9 and 30 for a payoff of negative 50. However, if that player had ended up with the 10 as well, the 10 would have joined the 9 to their existing run of 11 and 12, and their payoff would have increased to negative 39 instead of negative 50. We will focus on several different scenarios and calculate their Nash Equilibria. The first 2 examples occur in the middle of the game, and we will calculate the Nash Equilibria for that single round. In the third example, we will see the final round of a game. We will calculate the Nash Equilibrium for the single round and examine whether that Nash Equilibrium is the best response overall to help individual players win the game. For the ease of this game, in example 1, we are looking at only a few cards, and each player has enough chips that they will not run out. This means that the players can play a round until a player picks up the card by choice. We are looking for Nash Equilibria of this single round. For our first example, each player has 11 chips. The face-up card is an 8. Since player 2 has the 9 and no player has the 7, only player 2 can currently form a run using the 8. This means that only player 2 wants the 8, since it will only improve his payoff at this point. Any other player would significantly decrease their player by picking up the 8, because we would subtract 8 from their current payoff. We see for our extensive game modeling using the tree. Each circle has a label with which player's turn it is, and we start up at the top with player 1. I do want you to note that in this game, we could theoretically play until every player has used all 11 of their chips, and then player 1 would end up taking the card with 33 chips on it. However, once we get an equal number of chips to the value of the card, every player has a positive payoff by picking up the card. So it is in player 2's best interest to immediately pick up the card that they want, once 8 chips have been actually laid down on the card. Player 2 would not want the card to go around with more chips than 8, because player 1 or player 3 would then have a positive payoff by picking it up. Okay, so we see that in the bottom right hand corner. When player 1 says no, player 2 is immediately going to choose yes, because they don't want player 1 or player 2 to get the positive payoff from it and have an incentive to choose to take the card. Okay, so up at the top with player 1, if they say yes, their payoff goes from 5, which is what they have at the start of this round, from our 6 point from the card, and the 11 points that they have from chips. If they pick up the 8, they now have a payoff of -3. Player 1 does not really want to have a negative payoff, so they would probably say no thanks and put a chip on the card. Okay, then it's player 2's turn. Player 2 has the 9 and they have 11 chips, which is a current payoff of 2. And if player 2 takes the 8, they form a run, which gains them a point, and they now have an extra chip, so they have gained a positive payoff of 2 net. Okay, so their 2 plus the 2 is 4. But player 2 might be greedy and want more chips on the card, so they might say no thanks, and then play would pass on to player 3 and player 1, both of whom do not want the card. It would decrease their payoffs even more. And then player 2 eventually will want to say yes. Okay, since this is an extensive game, we use backward induction. Note that every player is actually going to continue saying no, because they would rather wait until the card has more chips on it rather than take a lot of negative points right there at the beginning. And player 2 wants to accumulate as many chips on the card, even though they already know that they want the card. In our second example round, the face-up card is still an 8. Player 1 has the card 7 now instead of the 6. So that is really the only change in this whole example. Okay, so now player 1 has an incentive to choose yes, since the 7 and 8 form a sequence, which means player 1 and player 2 are actually fighting for this card. If either player chooses no, then that player will lose a chip. This decreases their own payoff, but increases the payoff for the other player. So we see that if player 1 ever chooses yes, their payoffs are actually increasing and positive, which is fabulous for them. If player 2 ever chooses yes, their payoffs increase. If player 3 ever chooses yes, they actually have lower payoffs because it does not help them form a run. So player 3 should always choose no. The big difference in this then is that as we do our reverse induction, starting from the bottom, player 1 and player 2 are always going to want to say yes. So that means that player 1, in order to keep player 2 from taking the card, has to immediately choose yes for the Nash equilibrium. Example 3 is very similar to example 1, since only one player will want to say yes to the card. The face-up card 17 will complete a run for player 1, significantly increasing his payoff. In this case, only player 1 would benefit from taking the card. Take a look at the bold numbers on this. So it looks like player 1 should continue saying no so that the card will collect more chips, just like in example 1. However, since player 2 only has 2 chips, player 1 will need to say yes before player 2 gets a third turn, because at that point, player 2 would be required to take the card. So we see our payoffs here. Player 2, down at the bottom right, would be required to say yes to the card because they would have no more chips on their third turn. Using backward induction, since player 1 is the only one who wants the card, player 1 is going to wait until the very last minute to say yes, okay? Because then they get the best payoff from all of the chips that have accumulated. However, since this is the last turn of the game, we need to consider the point of the game. The player with the highest payoff is the winner. So it doesn't matter whether your payoff is higher than it was before, it just has to be higher than the other player's payoffs. So here, if player 2 allows player 1 to take the 17, player 1 will have the highest payoff and win. If player 2 takes the card, however, then he will win the game. So following the Nash equilibrium of the round is not actually a Nash equilibrium of the game, because player 2, we see in blue, actually has incentive to choose yes on his first turn, because his payoff would be negative 51, which is higher than either of the other 2 players' payoffs. So we have noticed that our Nash equilibria have some weaknesses. Okay? For reference, here are the Nash equilibria that we found. One of the weaknesses that we have found is that when players use most of their chips or all of their chips, that affects how many chips they have for future rounds. This causes one of the extensive games to be cut short, as in example 3. So player 2 was not able to build up as many chips on that card. Another weakness is that one that we discovered in example 3, where the Nash equilibrium of the round loses the game for player 2. Since player 2 could have won the game by not following the round Nash equilibrium, he has incentive to change his first action to yes. So the round Nash equilibrium is not necessarily the Nash equilibrium for him winning the game. Okay, the fact that one game of no thanks has multiple rounds affects whether players are willing to continue saying no thanks, since chip count carries through to the next round. In any of our example rounds, player 3 might get fed up with players 1 and 2 repeatedly saying no thanks on a card that they actually want. So then player 3 might just take the card that has a lot of chips on it out of spite, or to keep the other players from using that strategy of shipping the card around trying to collect more and more chips. Oddly enough, even though taking a card would decrease player 3's payoff, this might prevent him from losing more chips during that round, during the rest of the game, or during future games, which could lead to him having better payoffs overall. Randomization is another weakness of Nash equilibria for this game. Not only are 9 cards randomly and secretly dealt out, but the order in which the cards are revealed is random. As such, players do not have full information. A card that does not currently complete a run might eventually complete a run for a player in the future. So the payoffs could vary very, very wildly. In conclusion, no thanks does have individual Nash equilibria for rounds. However, following the Nash equilibria likely does not lead to winning the game. Thanks for listening.